So it's my pleasure to introduce my colleague and friend, Andrea Fanelli from the Institut de Mathématiques de Bordeaux, who will speak on rational simple connectedness and Fanon threefolds.
Okay, so thanks, Jesus, the other organizer. It's a pleasure to start, like say, the academic year in some sense with this talk. Today I want to discuss a project, a joint project with Laurent Grouzon and Nicolas Perrin. Okay, and everything I will say today will be overseen. Okay, so let me start with some kind of like the motivation in a sense. So this notion of rational simple connectedness is some kind of very tricky notion, and still like there is not, at least to me, a unique definition of that. Oh, so you can think of it of some kind of algebra geometric analog of simple connectedness in topology. Okay. But again, there is there is kind of a lot of literature on that. But if you look at papers, there are several definitions. So what I'll try to do today is like start from my point of view on this notion and try to give you an idea basically of some examples and how you can really like prove something on Fanon threefolds, okay, which is like some examples I like Fanon threefolds. So that's kind of a nice place to start with examples, okay. So, and let me start with, as I said, with some motivation. Of course, please feel free to stop me if you can, if there is a problem or anything, do not hesitate. Huh? So my motivation comes from birational geometry classification and the minimal model program. And so let me recall something that maybe many people know here, but I think it's good. So say that you want to classify up to birational equivalence algebraic varieties. So if you start with Z as smooth projective variety with a codaric dimension of Z minus infinity. So there is the very famous MMP conjecture. Implies that you can reduce yourself to study a very special class of projective varieties, which are Modifibration. So the MMP conjecture implies for this class of variety that Z is birational to a Modifibration. Okay, what is the Modifibration? So it's so let me just to fix the notation from W to be the base, which is if you want some kind of minimal. I will be a little vague here because this is not the point of the talk. It's a little bit of a motivation. Minimal Fanon vibration. Okay, so sorry, there are some noise here. I have to just email. All right, sorry. Okay. All right. So in particular, of course, the general fiber of this pi is rationally connected. This is a classical result by, well, Campana, Kolar, Mioka, Mori, and others in the singular case. Okay, so say in the perspective of birational geometry, so you kind of reduce yourself to these kind of modifibrations, and you can ask any reasonable questions on the structure of those vibrations, which is going to be interesting in a sense, right? And so the question I ask myself is a structural question on modifibration, which is about the existence of rational section. So does my pi here admit a rational section? Or if you want in more like algebraic terms, I mean, I'm just taking my W, take the generic fiber, okay? And I'm looking at rational points. And I'm asking if this set is not empty, okay? All right, so there is an easy, well, nowadays easy answer to this if the base is a curve. So a classical result by Graeber, Harris, and Starr which is 2003, this tells us if B is a curve, then pi has a section. So answer, positive answer for in the case where the base of this vibration is a curve. Of course, when you run the MMP, you have like no control on the dimension of the base. So you can try to, you can, of course, ask the same question if the base of this vibration is, say, a surface, but you immediately realize that there are plenty of examples where of Fano vibrations over surfaces which have no rational section. So if B is a, say, smooth surface, there are plenty of examples. Of Fano vibrations with no rational section. Okay. I think the example is conic bundles over P2, many conic bundles over P2. Okay, let me, just to fix ideas, I want to write down one example. Okay, so just to show you how easy it is to write down explicitly an example where of a Fano vibration over a surface which has no rational section. So you take inside P2 cross P2. So let's take a conic bund. So we write it so naught square plus. Okay. This guy is going to be our W, and then you fiber over P2 with the X coordinates, okay, XI coordinates. Okay, what is the picture of this? Well, you have your W here, you're fibering over your P2 here. Okay, and you see there is a curve of where the fibers degenerate, okay, which are exactly the coordinate lines here on the P2. So now if you take a point outside this curve, you get like a conic, nice smooth conic. If you take a point on, so general point on this curve, you will get two lines intersecting like this. And if you take the intersection, so the singular point of this curve here, you will get a double line. Okay. And this guy, this is like very easy example, sorry, it has no rational section. I open my pie, okay. So you see, okay, so at this point you say, okay, well, done, over, like there are plenty of counterexample, okay, but of course you...
Sorry, I have a question.
Sure.
Sorry, is it obvious that there are no rational section? Okay, we have
do it by
singular
hand.
fibers.
You can do it by hand. You can really like do it by hand, supposing that there is a rational point in this case, and you get a contradiction. It's not like obvious,
Okay.
like just looking at it, but you're right. I mean, you have to do like a little computation.
Okay, thank you very much.
Welcome. Right. Anyway, like the theory of conic bundles, it's kind of on conic bundles on P2 is like now classical, that like the work of Beauville, like, and you can really like, so a lot is known on that. So really, yeah. But in this case, you can really do it by hand. Okay. So let's get to the problem. Okay, which is trying to generalize. So this result by Graeber, Harris, and Starr in some sense when B is a smooth surface. Okay. And I want to start with some positive result. Okay, something giving us a little bit of hope in this direction, which is so a classical result, which is Sand-Lang theorem. And so it's in the 30s, 1930s, 1950s, I think, in Lang's version. And that's the result. It's about hypersurfaces. So this is also very classical and well known, but let me recall it. So fix the function field of B r-dimensional and take a hypersurface over this BK. So XD inside P, say, and BK, degree D hypersurface over K. Okay, and you ask for a numerical condition, so such that D power R is less or equal than N. N is the dimension of the projective space here, okay, and R is the dimension of the base of, okay, the dimension of this variety, okay. Then this guy has rational points, so XDK is not empty. All right. Okay. So this is nice, it's like interesting. So you see, look at the case R equal 1, okay? R equal 1 is exactly so hypersurfaces which are Fano, okay? So it's the Fano condition for hypersurfaces. So in that case, you get, so for R1, okay? So when, say, if you're thinking in geometric terms, in terms of vibration, you're looking at the generic fiber of a vibration over a curve, then you get a section. So if you want, Graeber, Harris, and Starr is a generalization of Sand theorem for arbitrary rationally connected varieties. Okay, let me, so what I said, I just like write it down, say. So case, so, okay, let me just, so let me just, so take XD inside Pn as smooth, say smooth to simplify. Hypersurfaces. Okay, and let's look at like Sand-Lang theorem for R equal 1, case R equal 1. Okay. So you see you have this numerical condition, okay, which is equivalent to be rationally connected. and is also equivalent to B Fano, so XD Fano. Okay, so in a sense, we want to do one step further and look at the case R equal to. Okay, so the numerical condition here is D squared less or equal than N. This certainly implies, and is stronger than XD Fano. Okay, and the question is, what do we put here? Okay, so we are looking for a geometric way to interpret this numerical condition, D squared less or equal than N for hypersurfaces, in order to generalize it to all Fano varieties. Okay, and here the idea comes. So this is an idea by Barry Mazur. And let me also mention the Young and Starr, who started developing this kind of this notion. He said that, so this guy here, okay, this one should be an algebra analog of simple connectedness. In topology. Okay, this is kind of it comes from topology, this idea. Okay, and so let me show you at least so far, like, no definitions. As I said, like, the definition of this notion is going to be complicated, but like, just let's take, so this is a little bit of a game. So let's take the definition of simple connectedness in topology, and let's see how we can generalize that, or I mean, find an algebra geometric analog of this. Okay, so let's take the definition in topology. So topology. Okay, so let me call you the definition of rationally simply of simply connectedness. So the topological space is simply connected if, okay, a way to see it, if the space of two base paths is path connected. Connected. Okay. This is one of the equivalent, like, definition. This is like, take this as the definition of simply connected in topology, and let's make it algebra geometric. Okay. Okay. So algebraic geometry. Okay. So here you will replace topological space with algebraic variety. It's going to be rationally simply connected. Okay. Okay, you need some replacement for the space of two base paths. Okay, and well, what you look at is the moduli space of let me be like, curve. Let me be very vague here, because of course, if you say, oh my God, moduli space of rational curves, I mean, there are so many. Okay, so but anyway, this is just heuristics here. Okay, I will give you like precise definition. Okay, but this is like what you want to replace. The moduli space of rational curves. Okay, and path connectedness, well, is going to be replaced by rational connectedness. All right, this is the idea, okay? Once again, this is just vague idea of how you come up with the definition, which I'll give you like in the next like 10 minutes, okay? All right. Also, let me mention that this is in a sense important. This is not the only way to generalize this numerical condition for hypersurfaces, which is, as I said, d squared less or equal than n, okay? There is another way to do that, and just to avoid confusion, let me mention this. So there are other possible ways to generalize condition d squared less or equal to n to Fano varieties. Okay. What is like another possible one? Well, you realize this, that if you take, so for hypersurfaces, this condition here is equivalent to asking if the second Chern character of X is positive. Okay, so this is just like a Chern classes computation. Okay, so you could say, oh, well, I take this as a definition, as like generalization to Fano varieties of the condition d squared less or equal than n. But here you come up with that complete, like another notion, okay, which is what people call in literature two Fano varieties. So Fano varieties with the second Chern character, which is positive, are called two Fano varieties. And then there is all the notion of higher Fano varieties, but I will not discuss this. But this is just to tell you that you can come up with other generalizations, okay, which are not like, so a priori are not equivalent. Actually, they're not equivalent to this rationally simply connectedness. Okay. All right. Okay, so let's try to write down a definition now, since we did a little bit of introduction for the moment. And so I want to give a definition. Okay. Okay, let me fix a little bit of notation here. So I fix X smooth projective. Alrighty. And I will need technical assumption, which, I mean, you can erase, but for this definition, let me assume this. So I ask that the Picard rank of my variety here is 1. Okay. This just makes more complicated. If you just erase this condition, you can still give a notion, some notions of rationally simply connectedness, but I mean, it's just a way to limitate the choice on moduli space of rational curves. Okay, so in this case, if the rank is 1, you just look at the degree of those rational curves with respect to the generator of the Picard. Okay. All right. Also, some notation I need to introduce this. So I will consider this is the Kontsevich moduli space of degree D stable rational curves with M marked points. Okay. Of course, this comes with an evaluation map. So let me always fix the notation. I have this on X power M. Okay. And what is the remark? Which is, of course, obvious if you want, but let me do it. In the case M equal 2, so the fibers of this evaluation 2 are exactly the analog in algebraic geometry of the 2 base path. In topology. So you see, we need to ask some kind of rational connectedness of the fibers of these evaluation maps. Okay, this is the point. And let me finally give you this definition. It's a long introduction. Definition. Okay, okay, this is really by the Young and Star. Okay. So I would say that X is rationally simply connected. I leave some space for a reason, huh? It's going to be clear later. So if, okay, what do we do? Okay, so you see there are many degrees, rational curves of many degrees you can look at. So what you want to say, we want some kind of asymptotic. Okay, so you just say, you look at moduli space for D sufficiently large, okay, for sufficiently large degree. So if there exists a D not, okay, positive, such that, so for all D bigger or equal than this D naught, okay, so even if you fix the degree, you have a priori several irreducible components of these moduli spaces. So what you want is a canonical component. There exists MD2, canonical component of M, so 0, 2, bar, X, D. Okay, let me also add this. So I will consider just the so the reducible components which parameterize morphisms which are birational onto their image. Okay, I will just focus on this. This is a little technical, but I want to do this restriction. This is the meaning of this beer here. Okay, and I look at the evaluation 2 from MD to X square, and I ask that this guy is dominant and the general fiber is rationally connected. Okay, let me just show the whole thing. Okay, maybe this is like the comment I want to do on this, something I write here. So parameterizing. Which are birational. Image. Okay. Okay, so already like this, it's kind of complicated. So let me repeat this. You take X and you say for D degree sufficiently large, there exists some canonical irreducible component of the moduli space, parameterizing curves which are morphisms which are birational to their image, such that if you look at the general fiber of the evaluation map, you get rationally connected. You get it rationally connected. Okay. Okay, so this is already like this, which is kind of technical. This is not even enough because you see there is some kind of strong version of rationally simply connectedness. So if you look at simply connectedness, okay, and you want to look at not just two-based paths, but M-based paths. If you have path connectedness of the case with two base points, so two base points, you automatically get path connectedness of the space parameterizing M-based paths. This is not the case for moduli spaces of rational curves. So it's not enough to just look at not enough just to look at two-based moduli space of rational curve with two marked points. So you need a strong version of rationally simply connected, of rational simple connectedness, which I will just add here. So what you ask is that for every M bigger or equal than 2, there exists some D naught depending on M, such that for every D sufficiently large, there exists, well, here you replace this with M, some canonical component of this moduli space, and here you replace with M, of course, such that, and here you replace the evaluation with the evaluation M points. So M, D, M, 2XM. And you want all these fibers to be rationally connected, okay? All right, so I know this is a little weird to digest, but that's the definition. Okay. While you look at that, if you want for a second, so I tell you what I want to do now. I would like to make some examples, giving you some results of rationally simply connectedness for some classes of variety, something which is known, and say some cases are known, some big classes of examples are known, but still very few, say, explicit examples been studied because it's very hard in general to understand the moduli space of rational curves for Fano variety. So not much, I mean, there are not many general results. And so what I'll do now is giving you these results and then study basically one example which is now clear to us, which is a Fano threefold, and tell you something about like our project and how we'll go on with that. Okay, so up. So examples. Okay, first one. Okay, of course, which one is the first one you should consider is PN. Okay, so the projective space. And this guy is strongly rationally simply connected. So let me just strongly rationally simply connected. Okay, I will just use the acronym, otherwise it's take ages. And why this is easy. So let me also give you like an idea of this. So when you want to parameterize, this is some kind of the first kind of exercise you do when you look at rational curves on projective varieties. So a degree D morphism. Okay, what you do is you fix M points. So you fix d plus 1 points. Let me call them y naught yd in Pn, and then you fix the same. So m, you need distinct points here, x naught xd in P1, and then you look at the space inside, so the morphism of degree d between P1 and Pn, parameterizing such that so the space inside parameterizing the morphism such that f, so this is f, I said fxi is yyi for all I. And this guy is rational. Okay, it's the rational to a projective space. This is very easy. And once you have that, basically you deduce the strong version of rational simply connectedness. So this is like quite specific, of course, to Pn. Okay. And for the second case, so one step further, still you can do it by hand. So let me maybe fix just to be coherent with my assumption n bigger or equal than 3, and you look at Qn inside Pn plus 1 quadric hypersurface. Okay, I just fixed n bigger or equal than 1 because I'm taking the Picard rank to be 1. Okay, that's why. Also, this one is strongly rationally simply connected. Okay, you need a little bit to be a little bit more careful, but basically it's the same like explicit strategy you apply for the projective space. Okay. See, and this is a result like the Young K and star. This is like very famous paper, and so the case of rational homogeneous varieties are so strongly, I put in parentheses, rationally simply connected. Okay, so I put in parentheses, I think you can deduce it. So the definition they have here of rationally simply connectedness is different. Okay, I'm sure that this implies the rational simply connectedness. I'm not sure about the strong version, but anyway, okay, so rational homogeneous varieties have been studied and are rationally simply connected. This is just a remark. This is a very famous paper because it's where they prove Serre conjecture 2. Okay, so these are about the examples. Another class of example, which is, so those are like big theorems, huh? So from C and D are big theorems. This is the Young and star. And I also mentioned the Land, which is a student of the Young, I think. So the Young and star, they have this paper, but it's, as far as I know, it's not published. And the Land, the paper by the Land is published. And so I will write down the statement of the Land, okay, this is about complete intersections, okay. So this is n bigger or equal than 3, and you take x dn inside Pn, so a general complete intersection of degree. So d d1 dc multi-degree, okay, and n is the dimension of the complete intersection, okay. So the result is that x dn is strongly rationally simply connected if and only if, and now, I mean, after the big introduction I made, it should be clear what is the numerical condition you get on the right side if we want this notion to be the right generalization to Fano, for Fano varieties of Sand theorem condition. Okay, so this is just the sum of the squares of the degrees is less or equal than being n. Okay, so in the case of hypersurface, it is exactly equivalent to d squared less or equal than n. Okay, which is what you want. Okay, but this is a theorem. Okay, to prove that this coincides for hypersurfaces to this. So this numerical condition here corresponds to this very tricky condition on the moduli spaces of rational curves. All right, just in parentheses, of course, this is not part of the theorem. Okay, but let me recall that this is equivalent to B2 Fano. Okay, this is just a remark. Okay, it's just the fact that this numerical condition on the degrees is equivalent to having positive second term character. Okay, good. So now I'm done with the examples, the kind of general results which are known, and let me move to smooth Fano threefolds. Okay. So smooth Fano threefolds, and let me also assume Picard rank of X. Okay. 1. Okay, so this is just, okay. Okay, I want to start this section with a theorem, which is by Araujo and Castravet. In 2013. Okay. Before doing this, if you look at Fano threefolds of Picard rank 1, so you have, of course, you have the classification of smooth Fano threefolds, okay, up to deformation, and you have all the families. And if you look at the families of Picard rank 1, you get 17 families, okay. And so the question is, okay, what if we look at those ones, and let's try to let's test this notion of rationally simple connectedness. Before doing that, you can say, oh, you should say, okay, what about this condition of 2 Fano, which is, at least in principle, easier to check because it's just a numerical computation of char characters. And this is the theorem by Araujo and Castravet. So X, smooth Fano threefold, and they classify in this paper 2 Fano threefolds. So X is 2 Fano, if and only if. So you have the list, and then you don't get many. You get just either P3 or the quadric in P4, and that's all. Okay, which is so you see, like this numerical condition is very, very restrictive. Okay, and those are basically the 2 examples we had before, right? Where you can check rational simple connectedness by hand. Okay, so and who should we look after those 2 guys? I mean, so the next guy in the list of Fano threefold Picard rank 1 is B5, okay, the quintic del pezzo inside P6. Okay, who is this guy? Okay, and let me also, so V5, so you take the Grassmannian 2,5, you embed this in P9, and then you intersect with P6. So you cut it with 3 hyperplanes. This is, okay, P9. That's the guy. And let me give you some information about this V5. So of course the Picard rank is 1. Okay, the Picard and the index, the Fano index is 2. So this is the H hyperplane, and the canonical divisor of this V5 is just -2H. Okay. Also, V5 is rational. So very close to P3 and Q3. Okay. V5 is not homogeneous, but quasi-homogeneous. So V5 is also quasi-homogeneous. Okay, so kind of close to all the classes I mentioned before. Okay, so you cannot apply the, say, general results. And here is where our contribution comes. So V5 is strongly rationally simply connected. Okay. Of course, clearly it's not too Fano. Okay, this is just the theorem I mentioned earlier. So in a sense, you see, those notions are different. Okay, it's not like for hypersurfaces where the two notions coincide. Okay, and in the time left, I just want to give an idea of how we prove this. Okay, we really use explicit birational geometry of this V5. So it's really like ad hoc method for V5. Okay, and so idea of proof. Okay, so let's take this M, let's say D beer. Okay, inside, let me just to simplify the notation inside M00 bar V5 D. Okay, I remind, this is just a reminder, this parameterizes morphisms which are birational onto the image. Okay. So we are lucky in a sense because there is, so the structure of irreducible components of moduli spaces of rational curves on this V5, it's not as nasty as it could be because so MD beer bar is irreducible. And this is a result, huh? It's not, this is a theorem. And this is by Lemon and Tanimoto. 2018. Say that this irreducibility comes also from our proof, but I mean, it's important to mention that, I mean, this was kind of known at the time. So what, say, we are looking for some rationally connectedness. So we need to prove that MD beer bar is rationally connected. Okay. So, and let's do some rational geometry on this guy. So take a line, a general line, L inside V5, and project from L. So let's look at this projection VL. So from V5, rational map, and you end up in P4. Okay, and so and actually the image of this projection is the quadric, dimension 3 in P4, and this guy is birational. Okay, and so let's make a little, like a picture. I'll do a picture of that. So right, so we have our L here. And then you look at, so what is the divisor which is contracted by this projection? Well, you take the lines through this line L, this divisor here, this DL, which is lines given by the lines through L, okay? And this is what is contracted, okay? So to so phi L of DL is, say, CL, which is a twisted cubic. Okay. And now you see we want to make some kind of want to compare the rational curves in V5 to some rational curves on the quadric, okay, which at least in principle will be easier to study. So take a degree, so CDC, a degree rational curve. So let me okay. You look at the image of the C here, it's going to be, you will get some rational curves intersecting this twisted cubic. So this is phi L of C. Okay. So what happens here, what I'm telling you is that phi L induces a map birational onto the image. So let me call it big phi from MD beer bar to M0 D, actually, the marked points, bar Q3 of degree D. Okay. So what, if you want to prove some rationally connectedness on the left, you need to prove some, it's enough to look at the image of this map. So, but this is like rational curves in Q3, which are easier to study. So we prove that this image is rationally connected. Okay, actually, we need rational. Okay, and so yes, this is the idea. Okay, of course, let me stress this, because you could think, oh, but yes, then you just reduce to if you know rationally simply connectedness on Q3, then you can immediately get rationally simply connectedness on V5. Actually, no, because this moduli space, this image of this map phi, is some special rational curves intersecting this twisted cubic. So there are some kind of condition which need to be studied. Okay, so this is tricky. Okay, but can be done because we're on Q3. Okay, so everything is can be made explicit. Okay, and let me finish up with some remarks, further remarks. So remarks. So to prove this is really like, I give you an idea, but of course there are many moduli space of rational curves which have to be studied. So to pass from rational simple connectedness of V5 to its strong version, we generalize, let me say, the techniques of the Young and Star and the Land to produce what they call a twisting surface. Okay, it's a little technical, but you can think of it as some two-dimensional analog of a very free curve, which is like gives you rationally connectedness for a variety. This is a rational surface inside this V5, which is in our case ruled by conics. Okay, so it's and so we cannot basically apply, this is a little technical, let me say this, you cannot apply the techniques by de Jong and Starr, which were developed for the case of complete intersections. And the reason is that in that case, they get a twisting surface, which is ruled, so it's ruled in lines, it's a scroll. But for V5, the problem is that you don't get this very twisting scroll. You need to look at, say, conic bundles inside your V5. And this is, so technically speaking, it's more complicated. Let me also say that another remark I want to make here, I'm really like up, okay, B, is about, so what about the other Fanon threefolds? Okay, so this is really in progress. So, and let me, so just comment on this. So if you look at, okay, so let's go through the list of Fanon threefolds, of smooth Fanon threefolds of pK rank 1. After P3, the quadric and V5, then you can go on with the index 2 Fanon threefolds. Okay, so in the index 2 case, so those cases have been, say, studied, and they are not rationally simply connected. So if the index is 2, the only rationally simply connected Fanon threefold is V5. If the index is 1, so what we think is that the only possible rationally simply connected Fanon threefold would be V22. Okay, I won't say much about this, but it's like another rational Fanon threefold, which is very famous for several reasons. For case stability, it's been studied a lot. But unfortunately, we cannot get any sort of rational connectedness of moduli space of rational curves on V22, because, so let's say our method cannot be generalized to V22, okay? The birational map from V5 to V22, or if you want, from Q3 to V22 is much more complicated, and we cannot just apply our methods. And so this is the thing. So I'd say that at least what we think is that the only rationally simply connected Fanon threefold of index 1 of pK rank 1 should be P3, the quadric, V5, and V22, maybe. Okay. And so hopefully I gave you some kind of idea of how you which are our methods. And again, once again, this is like a very, say, wild topic in a sense, because like there are very few examples, and so the idea of the project is really to study examples to better understand this notion. And I'm done, so I thank you for your attention.
Thank you. Yeah, I stop the recording for questions.